Giuliana. So I'm going to share my screen. Good morning, everyone. I'm very happy to be here with you today. I would like to begin my presentation with a question that lies at the core of my PhD work. How can we describe and formally represent a system of knowledge that emerged from the encounter between two different cultural and linguistic traditions? This is very reliable for my work because my research focuses on zoological section of Rerum Medicarum Novae Hispaniae Thesaurus, which is a major natural history of New Spain written by Francisco Hernandez in the late 16th century. A work that documents the encounter between European natural history and indigenous knowledge system and terminology. My aim is to study the zoological section of this work by analyzing how Hernandez classified and conceptualized animals in dialogue with classical models. On the other hand, I aim to develop an ontoterminological computational resource that allows this knowledge system to be formally represented using semantic web technologies. So two complementary but distinct dimensions are developed. A linguistic level which focuses on the extraction and analysis of terms, and a conceptual level which focuses on the ontological representation. In this presentation, I will focus on the first phase of the doctoral work, namely the linguistic dimension. I will show how I extracted the terms, how I standardized and organized them into a formalized resource, and how the structured foundation will serve as the starting point for the ontological modeling that will be developed in the next stages. So the first challenge was transforming an early printed text into a machine-readable corpus. The input I started from was the latent printed text, its digital scan, and the OCR recognition output generated from it. I did not produce the optical character recognition myself. What I received was the optical character recognition transcription extracted from the Internet Archive website. I needed, however, to implement a post-OCR correction workflow, combining manual revision and LLM-assisted normalization in order to produce a clean textual dataset. So the first methodological step consisted in addressing the quality of the OCR output. The text from Internet Archive showed a strong misalignment with the original and high number of recognition errors. In particular, the OCR system failed to interpret early model glyphs, such as the long S and several other signatures, resulting in a high character error rate. To solve this issue, I implemented a hybrid correction strategy combining manual philological revision and computational methods. I first manually corrected the most evident OCR errors. This process was then complemented by LLM-assisted post-OCR correction, which helped normalize orthography and reconstruct syntactic coherence while identifying historical typographic variant. In this workflow, the language model was instructed to operate as a digital philological assistant, correcting OCR, induced typographical errors, normalizing early modern graphic variants such as the alternation UV, EJ, and long S, and preserving the original lexical content of the text. The result is a normalized Latin text corpus in TXT format, which with a significantly reduced error rate, which provides a machine-readable data set suitable for terminological extraction. Once a clean and normalized corpus was obtained, it became possible to move to the next step, the extraction of zoological terminology. The goal of this phase was to identify not only animal species, but all terms directly or indirectly related to animals within the text. The dataset, therefore, as we will see, include different semantic categories. These slides present the workflow used for the extraction of zoological terminology. The process begins with prompt design, where the extraction task has been defined using a structured prompt with explicit linguistic and semantic constraint. The language model then has performed an initial automatic identification of candidate terms, following a high recall strategy in order to capture all potentially relevant animal-related concepts. The extracted candidates have been then manually reviewed and standardized, including lemma correction, part of speech verification, and ontological disambiguation. Finally, the validated terms have been organized into a structured dataset in Excel, which serves as the basis for further semantic analysis and the development of the computational lexicon. In order to obtain reliable results, the prompt used for the extraction was progressively refined through several iterations. I guided the model by assigning it a specific role, instructed it to act as a digital, again, a philological assistant for early modern dating, whose task was to extract the zoological terminology while preserving the original lexical forms. In the first phase, a broad extraction strategy was adopted to capture all potentially relevant animal-related terminology, including species name, anatomical part, habitats, etc. But after the examination of the result from the first chapters, the prompt was refined in order to better distinguish domain-specific terminology from purely rhetorical or generic expression. This led to a second version of the prompt, introducing clearly a domain term filtering strategy organized into three categories: keep, optional, and exclude. In particular, the exclusion criteria target very general or weakly domain-specific terms such as similes, absimile, or similar or dissimilar, or the word formas when used generically. By contrast, evaluative qualities such as horridus, terrificus, and monstrificus that have a very important part in the terminology of the wonderful in this medieval period were retained when they describe perceived properties of animals. The results of this extraction were then systematized in a structured tabular format. As you can see, each row corresponds to a single term and includes different types of information, combining linguistic, semantic, and contextual metadata. In particular, the table records the extracted terms, its normalized lemma, part of speech, language, an English translation, together with the textual reference, and when available, the definition found in the text, and additional fields document a proposed ontological and also class and superclass. And in addition to the linguistic and semantic information, the dataset was further enriched with visual documentation. As you can see here, an image is associated with the corresponding terminological entry, providing visual documentation of the animal described. Here you can see all the animals. Every images correspond to the original illustration included in the Hernandez work, and which were extracted from the digitized edition. The quantitative analysis of the dataset shows a clear predominance of nominal structures. Nouns, as it is shown here, represent about half of the lemmas and mainly refer to entities such as animals, anatomical parts, or natural substances. Adjectives are also frequent and mainly describe morphological properties of animals, reflecting the strongly descriptive nature of early modern zoological texts. Nominal phrases constitute another relevant component, often used to denote more specific concepts such as morbus gallicus, which means syphilis. Verbs are less frequent and mainly describe behavior or biological process such as hunting, hiding, or movement. So we can say that the grammatical profile of the dataset confirms the descriptive and classificatory nature of early modern natural history terminology. This slide presents the distribution of the extracted terminology across the ontological domains. In total, 10 domains were defined, covering the different areas of knowledge involved in the zoological descriptions. The largest domain are zoological and morphology, of course, which together represent a substantial portion of the terminology. This reflects that the central role of species identification, of course, and morphological description in early modern zoological texts. Other relevant domains include anatomy, medicine, animal behavior, and environment, showing that Hernandez's description integrate biological observation with medical knowledge and also environmental context. To better understand how this terminology is structured internally, we can also examine its distribution across ontological classes. As you can see here, the most frequent class, again, is animal, which includes the name of the species described in the text. It is followed by body part and morphological quality, reflecting the importance of anatomical description in the representation of animals. Additional classes such as habitat, disease, food, and substance show that the terminology connects animal with their environment and the substance derived from them. Overall, this distribution, we can say, highlights the semantic richness of the terminology organized around animals and their anatomical, ecological, and functional properties. These slides provide some examples of the ontological classes used in the dataset. As we have seen, many terms belong to the class of animal, which includes also animals used for comparison. this is very important. A large number of terms also belong to the class body part. The data set also includes other types of entities, such as human groups, disease, and medical substances. This class is very interesting and are interested in the example that you can see in red, which are lapis bezoar and oleum vulpinum. The first refers to a mineral, a stone concretion found in the stomach of certain animals and widely used in early modern medicine as an antidote. Oleum vulpinum, literally fox oil, on the other hand, was a medicinal preparation obtained from fox fat and used in traditional medicine for treating joint and muscular disorder. This slide, on the other hand, shows the linguistic distribution of the 510 terms extracted. All the terms were identified and then classified according their language in order to analyze the multilingual structure of the terminology. As the chart shows, Latin clearly dominates the data set. This, of course, is expected since the text is a Neo-Latin scientific work. In addition, I have to say that in the early modern period, Latin functioned as the main language of scientific communication, particularly in natural history and medicine. Most anatomical and descriptive terminology appears, of course, in Latin. But we have a smaller number of terms belonging to European languages, especially Spanish. Armadillo, caiman. These usually appear when the author reports vernacular names used by Europeans to refer to certain animals, but reflecting the knowledge circulation in the colonial context. However, one of the most interesting aspects of the dataset is the presence of Nahuatl terminology, a language historically spoken in central Mexico. In the colonial period, Nahuatl began to be written using Latin alphabet, which allowed indigenous terms to be incorporated into Latin scholarly works. In the text, Nahuatl terms mainly designate local animal species or elements of the natural environment, often referring to species that had no exact equivalent in European zoology. So Latin, Spanish, Portuguese, French, Nahuatl, the dataset can therefore be considered a multilingual terminology resource. Latin functions as the language of scientific description. Nahuatl preserves indigenous zoological terminology. European languages such as Spanish appear as vernacular mediation, and English used in the resource to provide modern definition. From the curated Excel dataset to computational lexicon. Up to this point, I have presented the process of extracting and organizing the zoological terminology from the corpus into a structured dataset. The result is a curated dataset in Excel, where each entry includes the extract terms, its normalized lemma, etc. This structured dataset also serves as the basis for the creation of a computational lexicon. As illustrated here, the table is designed so that a conversion script will transform the dataset into a RDF-based lexical resource following the OntoLex Lemon model. In this framework, each term corresponds to a lexical entry which contains linguistic information such as the canonical form and part of speech. And every entry will be linked to lexical sense, to a conceptual entity represented in an ontology outside the model. In this way, the terminology extracted from the historical text will be integrated into a machine-readable semantic structure connecting lexical data with conceptual knowledge. So far, I have presented the extraction of the terminology and the creation of the structural dataset underlying the computational lexicon. However, these terms are not simply zoological labels. Many of them encode a significant semantic and cultural complexity. A good example of this is the Nahuatl term axolotl. You can see this animal illustrated in these two images. Axolotl is a compound formed by atl, meaning water, and xolotl, which is the name of a god, and meaning Nahuatl cosmology, monster, dog, or twin. Hernandez rendered this term in Latin as lusus aquarum, which is a term included in the dataset, literally meaning play of the water. This expression does not reproduce the original morphology of the Nahuatl compound, water plus xolotl, monster, dog, or twin. Yet it reflects a conceptual interpretation of the term, because in Nahuatl culture conceptualization, xolotl can also intrinsically evoke the idea of play, but conceptually. In this sense, Hernandez's choice is not arbitrary. Rather than translating the word literally, he selects one of its conceptual association in order to mediate its meaning for European readers. This example illustrates clearly the linguistic and conceptual complexity of the terminology extracted from the text. The analysis presented so far has shown, in fact, that the terminology extracted from Hernandez's text is not limited to simple zoological labels. Many of these terms, especially those derived from indigenous languages, encode multiple semantic and cultural layers that cannot be reduced to a single lexical meaning. This raises a series of methodological questions. How can we model these terms? How can we represent polysemic indigenous concepts? And how can we capture the different semantic layers they contain? The next stage of my work, therefore, will focus on the ontological modeling of this terminology. A first ontology has already been developed, providing the conceptual structure needed to represent these entities and their relationship. In the next presentation, I will start exactly from the case of axolotl to illustrate how these concepts can be integrated into a taxonomic and semantic framework. Thank you very much.